Hello everyone, I'll be doing a question from Sp19 quiz 8. And that is, derive the magnetic field of the infinite coaxial cable with a non-uniform current density J as shown. The direction of the current in the inner conductor is coming out. Find B everywhere. So this equation will be using Ampere's law. Ampere's law is given by the integral of B field times dot product dl equals B naught I. So our first step is to figure out where to place our Amperian loop. We'll be finding using Ampere's law inside the region A, inside this radius right here. So this the smaller circle. Go ahead and create an Amperian loop inside the region A. And the radius of this Amperian loop can be given by just a little r. Right? So looking at the magnetic field between R and A, we go ahead and start that off. So we'll look at when R is less than A. We know that given by this equation up here. Integral B field times dl equals U naught I. This equation is also equal to the integral of B dot dl U naught integral of J dot dA, and don't forget your arrows on top. We know that again, B is the integral of the magnetic field around the loop. dl is the segments that make up the loop. Mu naught is the permeability constant, and I is the total current that passes through the loop. When we look at the equation right here, when I is equal to integral J dot dA, J is the current density, and dA is determined by finding where our current density is constant. Since J depends on R, we can break down the cross-sectional area dA into rings. So that means that the Amperian loop right here, you could create this into just many rings inside the circle. Break down to many rings. Right? So go ahead and plug in some numbers into this equation. We know that since this is a dot product, it'll just be B times dl. dl is the dl is the segments that make up the loop. It'll just be 2 pi r. Mu naught is the permeability constant, so we just leave it as mu naught. I have here the integral J, which is our uniform current density. It will be 2r. And then dA is, again, the cross-sectional area. So it would be 2 pi r, which is the area of a circle, times dr. So 2 pi r, which is the length, dr is the width. Again, length times width gives us the area. So go ahead and simplify 2 pi r equals mu naught integral. We'll go ahead and multiply this out. 2r times 2 pi r times dr will just give us 4 pi r squared times dr. Since 4 pi is a constant, we could go ahead and move it over to the left of the integral. And we'll be integrating from r to 0, since we're looking at when r is less than a. Simplifying it out again, or integrating from r to 0, we'll go ahead and have 4 pi mu naught r cubed over 3. I'll go ahead and bring the left side down, b times 2 pi r. Go ahead and solve for b. b equals 2 mu naught r squared over 3. And since the current is coming out of the page, we'll go ahead and use our right hand rule to define the direction of our magnetic field. Your thumb will be pointing out of the page, since that's the direction of current. It's coming out of the page, and when you curl your fingers, that's the direction of your magnetic field, which is going counterclockwise. Next, we'll go ahead and find the magnetic field between A and B. So between A and B, we'll go ahead and make an Amperian loop inside the region B. It's the same distance R. So I'll go ahead and write right here, when A is less than B, or less than R, less than B. Go ahead and bring down the same equation right here. We have the integral of B magnetic field times dl equals mu naught integral of J dot product dA. Working on the right side only, mu naught integral. This is the dot product. We'll go ahead and we know that J is equal to 2R. And again, the cross-sectional area, which is 2 pi r dr. And that just multiplies that out. We get u naught integral and 4 pi r squared dr. We're going to bring the 4 pi to the left side, since that is a constant. 4 pi mu naught integral r squared from dr. For this Amperian loop, we'll be integrating from 0 to a, because b is in the region of air. It's given by there. See, b is in air, so it'll be from 0 to a, or is our integration. I'm just going to bring this up right here. We have here b times 2 pi r. Again, that is our dl there, which is the same as 2 pi r, equals 4 pi mu naught. We have r cubed over 3 from a to 0. And then go ahead and simplify that even further. We get 4 pi mu naught a cubed over 3 times 2 pi r. And we'll solve for b, which we have here. B is equal to 2 mu naught a cubed over 3r. Again, this is in the counterclockwise direction. Next, we'll go ahead and find the magnetic field when r is greater than b. So it'll be on this Amperian loop right here when r is greater than b. We know that the C radius is a conductor, so we know that B is equal to 0 because it is grounded and shielded. Anywhere that r is greater than b, so it's on the C radius, it's a conductor, and anywhere above that is grounded as well, so there'll be no magnetic field. So again, to recap, when r is less than a, we have our B field right here, which is B is equal to 2 mu naught r squared over 3 in the counterclockwise direction. When r is between a and b, we have here the B field equals 2 mu naught a cubed over 3r in the counterclockwise direction. When r is greater than b, we know that b is 0, and that is because it is grounded and shielded, which can be represented right here in the diagram.